These are the notes for Unit 7, Day 4. And so the previous day we learned about important features of the graph of the polynomial. So in yesterday's activity, right, we have this anchor chart, and you determined some really general conclusions. So let's first summarize those conclusions. So what we learned, I'm going to use the same color coding, is if we know the degree, we can determine that if it's odd, that the ends do different things. Right, one goes up, one goes down. If it's even, the ends do the same thing. They both go up, both go down. So like down here, this must be even, right? Because the ends both do the same thing, they both go up. And then we looked at the leading coefficient. And the leading coefficient, if the leading coefficient was positive, then the right side goes up. And that means that, and so what we are able to do then is, if we know if the leading coefficient is positive, that means the right goes up. Like this down here, this leading coefficient must be positive because the right side goes up. Then we can go back to the odd and even scenario and determine what happens to the left side. And then conversely, if the leading coefficient is negative, then the right side goes down. And then again, we can look back at the, so like this. The right side would do something like this, right? So, and then we can look back at the degree and conclude what happens to the left side. And then the other thing that we determined is that based on the degree, again, going back to this degree, that's at most the number of x-intercepts. So if we have a degree of 4, we have at most 4 intercepts. We could have fewer, but we won't have more. Okay, so it says use the function to answer the following questions about it. So we have this function here, and it looks like here's our leading coefficient. It looks like it's written in general terms from big power to low. So we know our degree is 3, and so at most 3 x-intercepts. Right now it's hard to say what they are because we don't have the factored form. And then it says, it's asking us to graph the function now, and let's see how many we actually do have. So we're going to put this in, x cubed plus x squared, using my squared key, minus, whoopsies, minus 5x plus 3. And when we graph that, we see one intercept right here at -3. So we have an intercept at -3, and we have an intercept here at 1. So we only see 2. So we don't have 3 like the degree would indicate. So let's graph this. The graph really didn't copy well. We should have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, this didn't really copy that well. Okay, so we have an x-intercept at -3, which is right here, and +1. And then we have something that looks like going through -3, bottom to top, and then coming to +1, but not going through per se, but kind of touching 1 and going back to the same side. That's a special characteristic. Okay, we know that as a repeated root. So what we have then, if we go back and annotate this a little bit better, this is repeated. In other words, it counts twice. So if this counts twice, and this counts once, then this technically gets us back to our 3 to measure our degree. Even though we don't actually physically have 3 intercepts, we can see that we have a 3rd degree polynomial because we have one repeated root and one not repeated root. Okay, so now we notice we go on to part D here. It says the equation above can also be written in factored form. So this gets us a lot of really good stuff here because we have the factored form. And now we can see the repeated roots by seeing the repeated factors. Okay, so when we look at this factor x minus 1 and set it equal to 0 to find our zeros, we add 1 to both sides, and we get x equals 1. And then we can do the other unique factor, x plus 3, set it equal to 0, solve it, and we get x equals minus 3. So we can see that because this is repeated, right? In other words, I'm going to erase that. And I'm going to erase this. In other words, it's literally repeated. Like I could come over here and do x minus 1 again, right? I mean, I would just be duplicating the steps over that I have over on the right. So we can see that there are actually 3 zeros, and they are x equals 1 and 1 again and negative 3. So there are actually 3 of them since we have that repeated root. So what we've noticed then is we have this characteristic, and we looked at, I'm going back and seeing the section, I think it was day 2. Yeah, it was the day 2 homework where we first were introduced to those repeated roots. So if it's back a couple of days. Okay, so let's take a look at this next one. So we're going to graph this one. We have, oops, there we go. Clear this out. So we have 0.5 x to the 5th, x to the 5th. Looks like I gotta delete some stuff here. There we go. Plus 3x to the 4th. So to get those powers, I'm using the caret key above the divide key. Plus 3x cubed, because all of those degrees are bigger than 2. And then once I get to the minus 8x squared, I do have an x squared button. So I'm going to use that. Minus 7.5x. Holy cow, plus 9. There we go. Okay, I have a calculator error. Interesting. That was a long function. Let's see here. Let's go back here. 0.5x. Oh, I've got 2 plus signs. There it is. Plus, plus. We don't need 2 plus signs. There we go. Okay, now I can graph it. So I've got something that looks like this. I'm just going to squash it vertically a little bit so we can get it all on the graph. So what is the degree of the function? Looking just at purely at this, at the equation itself, we know the degree is 5. That's that highest power, and it's written in general form, so it's the first term. How many x-intercepts do you expect there to be? At most 5. At most it's going to match the degree. Graph the function. How many do I see? So I see an x-intercept here. It's a repeated root. So that's negative 3. And then here at negative 2. So I got to do the same thing here with my graph. I have to fix it. 1, 2, 3, 4, 5. Probably not the best at making these hash marks. There we go. So let's kind of start over here. We've got an x-intercept at negative 3. Again, right here. And an x-intercept at negative 2. So really close together. And then a repeated one at 1. So we've got a repeated one at negative 3 and positive 1, right? We can see that we go up to negative 3 and then turn around. We don't cross through. And same thing here. We come down to 1 and then go back up. We don't cross through. And then at negative 2, we cross through. So that's a single root. So we have something that looks like come up, hit the repeated root, go through, come back. Whoops, didn't go fast enough. Let's try that again. come up, bounce back down, go back up, bounce back down. There we go. So it looks something like that. And so we physically see 3 intercepts, right? 3 intercepts. They are -3, -2, and +1. But notice the factored form now. So in part D, I've got the factored form. It's written a little bit differently. Instead of listing out every factor, because I should have 5 factors, I should have some repeated, like I did here, right? We repeated the factors up here in 1D. Instead of repeating the factors, I used my power instead. So this x minus 1 squared, this x minus 1 squared really means x minus 1 times x minus 1. And this x plus 3 squared really means x plus 3 times x plus 3. And then we have a single factor of x plus 2. Notice we know what a is. Remember how we are always leaving that as a? We know a is 0.5. We can actually even see it here, right? A is 0.5 in this case. So we know we really have 1, 2, 3, 4, 5 zeros in all reality. We have 5 zeros, and they are x equals -1, not -1, excuse me, x equals 1 and 1 again, and -3, and -3 again. They're just out of order. I confused myself. And -2. So those are the actual zeros. So we see it. We have a few repeated, and so we know from the graph. So this is, how can you tell from the graph? We know that repeated roots. Okay, if they're squared, the repeated roots then will come down. Let me make that black actually, so it looks more like an x-axis and a y-axis. Repeated roots will come down and move and bounce back up, or come up and bounce back down. This is for an even root. Okay, so the even roots are really easy to see. Okay, because they bounce like that, the repeated roots. If it is odd, if the root is odd, the repeated root is odd. Let me change the color here. If the repeated root is odd, which we haven't discussed yet, this actually just looks like a regular root. It's harder to see. So it looks normal. It doesn't bounce, it goes through, just like a regular root. If you know, a single root is just repeated once, right? So that's an odd number. So these are harder to see. That's why we focus on the repeated roots being even, because they're easier to see. So our focus is really, let me change colors here. Our focus is really here, seeing those repeated even roots. So I can get rid of this graph now. For our learning targets then, we've got 2 of them. And our first learning target is that we have repeated roots or repeated zeros. That means the same thing as roots. I'm going to use the word zeros because that's what shows up on your graphing calculator. So a repeated root looks like x minus p to the power n. And if n is even, then I'm going to change that to green, because we were using green as the even repeated roots. Actually, I think I might change this to blue. There we go. Okay, so if n is even, then we know we have something that looks like this. Whoops. Let's make that a little more precise. Or this. And if n is odd, now I'll use red for odd. If n is odd, it's harder to see. We have something that just goes straight through like a regular root, like this from top to bottom or bottom to top. So those are hard to see. And And then the other thing that we haven't talked about yet, but we're going to talk about it down below, is if we have imaginary roots. So if you remember imaginary roots, our complex form looks like a plus bi. And then we have this conjugate that looks like a minus bi. And so our imaginary roots would be like x equals b to the b times I. That would be a imaginary root. And its conjugate then, so we have a conjugate of x equals minus bi. And those always occur in pairs. So these always occur in pairs. So what we're going to do is we're going to discuss down here, this check your understanding. I don't know why they're both labeled 1. We're going to call this question 2. So a polynomial function has real coefficients and zeros, x equals 2 and x equals 5i. So if these are two zeros, then the missing zero that's not listed above is x equals minus 5i. It's that conjugate. And so a possible, back to writing a possible polynomial. So that's the y equals a, and then we list all of the factors. So the first factor is x minus 2, the next factor is x minus 5i, and then the last factor is x plus 5i. And that's a possible polynomial. Now, general form we're not going to worry about, but we do need to write this as a real form. So we want to make sure we have real factors, and we don't right now. So what we're going to do is we are going to multiply out, the imaginary factors, because that's going to turn them into real. So we're going to multiply imaginary factors, and I'm going to do that using an area model. So we're going to have x minus 5i, x plus 5i. We're going to multiply this out. This is x squared, right? X times x is x squared. X times negative 5i is negative 5ix. X times positive 5i is positive 5ix. And negative 5i times positive 5i is negative 25i squared. So we know that the like terms are these, and those cancel. These cancel. Running out of space. There we go. Those cancel. And so we are left with x squared minus 25i squared. But remember, 25i squared is a real number. That's x squared minus 25 times negative 1. So that's x squared plus 25. So we have to write this as y equals a x minus 2 times x squared plus 25. We have to make sure that those factors have are real factors, not imaginary factors. Okay, so as you work on the homework, you'll have that scenario here, and you'll have that scenario here where you have to multiply those out to get those factors to be real expressions, not imaginary expressions.